Hello and welcome to this video presentation, this WebEx video presentation for the Temple University NASA Lunabotics 2014 electrical team. This is a WebEx posting that is due Monday, December 2nd. Hello, my name is Mark Halberstadt. I'm a member of the electrical team for the Lunabotics team. On the team is myself. My name is Mark Halberstadt. And also Eric Schisselbauer and John Morris. And our faculty advisor is Dr. John Helferty of the Electrical and Computer Engineering Department at Temple. So what I want to do in this presentation is I want to recap the electrical team goals the overall goals that we have for the project, show our overall progress, and then finally I want to run through what the next steps are for the project. So to start off, these are our overall team goals on the electrical science, and really these are remaining constant. These are the same goals that we've had since day one. We're designing and building power, control, and communication systems capable of powering and driving a mining vehicle through a harsh lunar environment. That is our primary number one absolute goal. Below that, our kind of second goal, it's still very much a primary goal. We want to have complete autonomous functionality of our mining vehicle. And then the third goal is we want to make the most efficient system that we possibly can. A big part of that is really going to be measuring how efficient our system actually is, such that we might be able to reduce the size of weight of specifically our power system and specifically our battery that's really supplying power to the entire vehicle. In our previous video, we outlined a schedule where we said by November 22nd that we would be able to read electrical current data from a current measurement device into an Arduino, that we would be able to implement a TCP/IP server on the Robot Control Center, and that we would be able to conduct initial testing on essentially what is going to become our localization system that's made using Nintendo Wiimotes. Unfortunately, there's still a good amount of work that is left to be done in all three of these areas. Progress has been made into all three of these areas, but we cannot say that we are 100%, that this has been 100% accomplished. Our TCP/IP server, we do have programs right now that are sending bits of information between a server and a client. However, we don't have that interface yet the exact way we want to. The big goal for this was to be able to essentially implement manual control on our testing platform, such that we could, use a joystick to control our autonomous testing platform. That still has to be done. We've actually done a lot of work on a current measurement device, and really the reason that this is not completely implemented yet is because we kind of ran into sort of an unexpected problem that it might make it so we might not be able to use the device we were planning on using. And we still have to do more testing in order to get the particle filter to work for our localization system. So most of this work that we're doing really concerns our autonomous lawnmower testing platform that the electrical team, very graciously, the autonomous lawnmower team from last year allowed us to use their platform for us to do our testing. And really, most of the work we're doing is still concerning this platform. We are trying to be able to measure the current that's coming out of the battery accurately on this platform, such that when we move this to the robot that's being developed by our mechanical team, we'll be able to accurately measure the current that's being consumed by that new system. We are also trying to implement manual control, and we are also trying to implement some autonomy using this testing platform. So now, kind of the new stuff that we've been working on, and really the most progress that has been made is on the current sensor that's essentially going to measure the current, and really it's going to measure both current and voltage coming out of our battery, and that's going to give us a very accurate reading, or hopefully it's going to give us a very accurate reading of power. This is the Autopilot current sensor unit that this was used by a previous Temple University Lunabotics team in order to measure and report current consumed by the robot. And as you can see here, this device is rated for up to 50 volts, which is more than the amount of voltage we'll be using it for. And we can also draw 90 amps through this device accurately. Essentially, there is a current measuring shunt right here that is 1/2 of a milliohm. And essentially what the output is we get analog voltage output for both current and ground. This analog voltage ranges between 0 volts and plus 3.3 volts above our ground reference for both the current and the voltage measurement. So 0 volts on the current output means that no current is passing through the device. Plus 3.3 volts essentially means 90 amps of current is passing through the device. There's a very similar scheme, and also another challenge is that the response of the current is it's approximately linear, but we are going to have essentially a lookup table because it's not exactly linear output that we get. From the voltage, we get very similar behavior. 0 volts output with respect to this ground on this voltage output pin corresponds to 0 volts of potential difference between this ground of our battery and our positive voltage lead, and plus 3.3 volts output from this voltage pin corresponds to 50 volts. We've done some testing with this device, and essentially the problem that we are having right now is this. This is a graph of the data that we've recorded from this device. So our x-axis that we have, or our horizontal axis, is the current which was put through the device. So we put through 0 to 3 amps. We obviously have to do much more testing that will extend beyond 3 amps because we're really planning on consuming probably around 25 to 30 amps of current for our device. But pretty much what we have is current on our x-axis, our horizontal axis, and our y-axis we have output voltage that's coming out of our current sensing pin. And essentially you can see here that before we get up to 1.5 volts, essentially, we have this response that it might be kind of difficult for us to use. If we can tell, if we are using approximately 0 amps, or we might not care that much if we're using below 1.5 amps, but probably I think we're going to care that we're using below 1.5 amps. Basically, we're going to have to deal with this, with the fact that we have got essentially 2 different responses for our current measuring unit right now, depending on whether or not we are consuming more than 1.5 amps or less than 1.5 amps. So that is this is sort of the results of what we have done with this particular unit we have. And really, pending the results of this testing, we might actually need to change this unit. This unit is actually, it's made by it was purchased from the Spark Fun catalog. The same catalog has another unit which will work up to 45 amps. We are planning on consuming or on drawing way less than 90 amps through our current measuring probe. Our batteries right now are rated to draw 90 amps of continuous current. Really, we should not even be approaching that. We are probably going to be drawing between 20 and 30 amps out of our battery at any given time. So we are probably going to be exploring in the near future the possibility of using the 45 amp model of our current measuring probe. So anyway, on to some other things which we have done. We have one of the things that we've been trying to do is Portions of our team, namely myself and my colleague Eric Schisselbauer, did some pretty extensive work for the Lunabotics project in the past. And what we have been trying to do is figure out a way, if we can, a way that we can reuse much of the code, the computer code that was developed in the past. So one of the things that I guess I'm happy to report is that much of the code is going to be reused, and this is actually a bit of a computer simulation, or it's I guess it's sort of a simulation. It's not really that much of a simulation, but essentially this animation shows. A simulated lunarena, which is going to turn into the visual output from our autonomous system. And we have gotten this running on our Raspberry Pi control system. Essentially, what this is doing is it's taking input information from two Wiimote sensor units and a compass unit. Right now, this is just completely simulated. This is not actually taking in either Wiimote data or compass data. This is just essentially simulated input data. But based on that simulated input data, a path is being computed using a version of the A-star algorithm. We are using an A-star algorithm, and right now there are no obstacles in this simulated arena. But we are essentially using this A-star algorithm to plot a path between the center of our robot and whatever target we are looking for. As you can see in this simulation, we have a dump target, a dig start target, and a dig finish target. Right now, and as you can see right now, our robot is essentially being navigated towards our dig start target. The A-star algorithm plots out this path, and then we are actually using an algorithm called an algorithm that's essentially derived from Brazenham's line algorithm in order to simplify this path into essentially a non-pixelated version, essentially a version where we'll be able to point the robot in a given direction that is not either exactly north, south, east, or west, and drive the robot directly to a target that we are looking for. So anyway, this has been implemented, and we have gotten this running on the Raspberry Pi. So we are hopefully going to be able to reuse the vast majority of the code which was developed for this project in previous years. Another thing which we are currently working on is this team, the electrical team, is a subset of the entire Lunabotics team, which includes both an electrical team and a mechanical team. The mechanical team is currently putting their finishing touches on their first prototype. And essentially, the electrical team is going to begin supporting that, and we are planning. We are hopefully going to be able to integrate a control system that's going to feature manual control, pretty much the same exact manual control that we currently have working on our autonomous lawnmower testing platform. That's just a simple GUI that'll drive the device forwards, backwards, left, and right. And then once we get our actual manual control with a joystick working on our autonomous testing platform, we will be able to move that manual control onto the mechanical team's first prototype. So anyway, to finish up, the next steps we really have to accomplish the goals that we had set for ourselves previously. Our power system, we have to do a bit more testing on our current measurement system, and if we deem that we really do need to go with the 45 amp version of the Autopilot, or if we need to go with a completely separate system, those decisions are going to have to be made, and we need to be able to integrate the current measurement systems into our testing platform, and then eventually into the first mechanical prototype. For the communication system, as I said, we do have essentially programs right now that are able to move bits back and forth between a client and server. However, we do need to optimize that such that we can get it to work with a joystick and get it to work with manual control. We also need to complete the data filtration and the particle filter system that's going to be working on our Wiimote localization system. So essentially, we want to be able to accomplish those goals that were pretty much outlined. And the big thing, and I guess the big difference is we're going to add that we want to have manual control with a joystick implemented for both our testing platform and have the possibility of very easily moving that to the mechanical prototype. Our goal for this is December 21st of 2013. And we are also going to set a goal for ourselves of January 10th of 2014, where we are going to integrate in obstacle detection sensors into our autonomous lawnmower testing platform, and we are hopefully going to have our first fully autonomous testing run using our autonomous lawnmower testing platform by January 10th of 2014. So this is 11 days before the start of the spring semester at Temple. So we are hopefully, what we want to do is we want to say that we are going to have our first autonomous testing run by January 10th, and then we are going to use the time between January 10th and the start of classes to work out as many of the bugs in our autonomous system as we possibly can before the start of the spring semester. So anyway, those are our goals and our next steps, and that concludes this presentation. Thank you so much for taking the time to watch this. Again, my name is Mark Halberstadt, and please, if you have any questions, please feel to leave comments in the WebEx video, or this is also going to be a YouTube video, or please send me email at c.mark.halberstadt@temple.edu. Thank you so much for watching.